I mean, this is just a problem. 4 secant theta tangent theta, the integral from negative pi over 3 to pi over 3. They just give me that. This is one of your homework problems. 4 secant theta tangent theta. You're integrating with respect to the variable theta, and you're going from negative pi over 3 to pi over 3. So this is different. I mean, this was a lot of work. I mean, this was a paragraph that said, find this area. And you had to sketch the curves. You had to figure out the region. You had to figure out the bounds. You had to set up the integral. I mean, you had a lot of work to do to find this area. This is just, do the integral, please. You can interpret it as area if you want to. You could go draw pictures if you want to, but that ain't the point. Can you just do the integral, please? So step 1 is the antiderivative of secant theta tangent theta. And she said secant. The 4 doesn't bother me. The 4 is a multiplied 4. I can sort of pull it out and then put it back. So I'm doing the antiderivative of secant theta tangent theta, which is secant theta times 4. Now, how do I know that? Because the derivative of secant theta, the derivative of secant theta is secant theta tangent theta. So the integral of secant theta tangent theta is secant theta. Whew. That means I know my derivative rules. I mean, if I know my derivative rules, I can do some of these antiderivative rules if they're nice like this. This is nice. Are you following me? I didn't do any tricks there. The derivative of secant is secant tan, so the integral of secant tan is back to secant. It's just memorized. So it's done. It's memorized and done. And now I gotta plug these numbers into it. Nobody likes this because people don't like trig too much. But you gotta plug in 4 times the secant of pi over 3 minus 4 times the secant of negative pi over 3. You know, I happen to know those. Well, I don't know what you would do. Maybe you'd pick up your calculator. Maybe you know your way around a unit circle. You know, it's 60 degrees. You know, I don't know the secant of 60 degrees until I do this. What's the cosine of 60 degrees? 1/2. So the secant is the reciprocal of cosine. So if the cosine of 60 is 1/2, the secant is 2. Do you know all that? Did you hear me? You might not know that, right? Some people are a little weak in their trig. So when I start talking trig, I lose you a little bit. Well, listen. If I lose you a little bit, you can pick up a calculator and ask for the secant of pi over 3. But you don't have a secant button. So how are you going to do it without a secant button? You're going to do 1 over cosine. And you're going to put it in radian mode, and you're going to type in pi over 3, I guess. Unless you know that pi over 3 is 60 degrees, then you can put it in degree mode and type in 60 degrees. I mean, you got a lot of options. Where just whatever knowledge you have, use it to your advantage. But I said, what the hell did I say? I forgot now. I know that the cosine of 60 is 1/2. I just happen to have that memorized. So the secant of 60, the reciprocal of that is 2. So this is a 2. Times 4 is an 8. Minus, what is this? This is negative 60 degrees. You know, then when you're at negative 60 degrees, I think the cosine is still 1/2.
Still positive.
It's positive 1/2. You got to get the positives and negatives right. Your calculator could help you with that. But this is the cosine of, or the secant of negative 60 degrees, which is still positive 1/2, or no, Jesus. The secant is still a positive 2. If that's a positive 2, what's this answer?
0.
0. That's okay. That's a 0. That's a fancy way of saying 0. That's just 0. Does that bother you? When you do an integral, the answer to an integral can be a number. When you do these are called definite integrals now. They have these bounds. The answers to these are going to be a number. These are a number. And the number can be interpreted as area under a curve if you want to. You don't always have to think like that. This number can be a positive number, a negative number, or a 0. I mean, it can be any number. This one happens to be 0.
I thought definite integrals had to be positive.
not negative.
Because of the area under the curve concept?
Yeah.
Or why?
5, 3.
Well, right.
Yeah.
Once you start cranking out these integrals, that it's a number, you can interpret this number as, this one happens to be a 0, you can interpret it as area under a curve. That is kind of what I was saying. But so, and then you think, well, area has to be positive, maybe. But I explained something the other day. I said this the other day, and maybe it needs to be said again. What an integral does is it treats any area below the x-axis as negative area. So that's why you can get a negative number when you do this. If the graph of this sits below the x-axis, then it's going to spit out a negative number. If the graph of this sits above the x-axis, it'll spit out a positive number that represents area. If the graph is below the x-axis, it spits out a negative number that represents the area. So how the hell do you get a 0? Maybe some of this graph is above the x-axis and some of this graph is below the x-axis, and we get a net result of 0. Are you with me?
Yeah.
So that's the truth. That's the truth, and I don't really know what this graph looks like. I'd have to go graph him, which I'm not sure what he looks like. But if I graphed him from negative pi over 3 to pi over 3, I'll just kind of guarantee you that it's from negative pi over 3 to pi over 3. What's happening is some of it is above, some area is above the x-axis, and some area is below the x-axis, and we get a net result of 0 in this problem. The truth is, though, now hang on. We're working on area. We are working on area. But at some point, you get up in there into 5-4, and somebody's just asking you to do integrals. Do this integral. Do this integral. Do this integral. And you don't have to stop and sketch and think about area. You don't have to. You just got to do it. And it's a definite integral with bounds. In the end, it'll come out to be some kind of number. And if you want to, when you're done, you can think about what that number means, and it does mean area somehow. But are you with me? All right. All right. So, I want to show you this. There's a lot more stuff to do, and maybe there's some stuff in 5-4 I didn't do, but I want to show you this. I got about 10 minutes left in class. Let me show you. I'm going to push you into 5-5. I'm sorry, but I got to show you this. I'll do more of this. What's today? Wednesday? Okay, I'll do more of this Friday, but I like to push ahead. You know me. I might have to back up too, but check this out. This is watch this. This is so cool. So this isn't back to an indefinite integral, if you don't mind. I can put some bounds on here, but it's an indefinite. I can do indefinite integrals, or I can do definite integrals, right, you guys? They have bounds or they don't have bounds. When it has bounds, it's a definite integral. The answer is a number. When it doesn't have bounds, you do your integration. You put a plus c. The answer is like a family of functions, or a right. Okay, all right. But you have to do the antiderivative, and so this is weird. You might not know how to do this antiderivative. It's what? Any suggestions? You could cube it out, right? You could FOIL it all out. Then you'd have a bunch of different terms, and you know how to integrate a bunch of different terms. Okay, I don't want to cube it all out, right?
Yeah.
Listen, so essentially, isn't it just something cubed?
Right.
And so maybe I can just do something, maybe I can just pretend it's a power rule. If it's something cubed, can't I just do something to the 4th divided by 4? I can. But technically, I can, dude. I mean, the answer is going to be this. X plus 4 to the 4th divided by 4. Basically, I'm thinking of it as something cubed, so this is how you do it, plus c. Are you with me? All right, now guess what? If I tried that on this, it wouldn't work. Watch this one. Watch this one. If I tried that on this one, I'd be a little bit wrong. I mean, so what do you, based on what you just learned, what do you want to say the answer is? 5x plus 8? It's just something to the third, so call it something to the fourth, divide by 4. See, I'm teaching you wrong. I'm sorry. This is wrong.
Right. Because you have that inside.
Oh.
Probably that 5.
Because the 5.
Oh, you're worried about the 5. Yeah, good. You guys are smart. I knew you were smart. You just got to listen. Thank you. Listen. You're worried about the 5. Now listen. So maybe somebody said multiply by 5 because you're doing a chain rule. But whoa. Chain rules are for differentiation or derivatives. I mean, we're doing antiderivatives, so maybe we do sort of an opposite of a chain rule. I mean, we don't do a chain rule. By the way, we don't do product rules and quotient rules and chain rules really in anti-differentiation. We don't have those rules. All right, let me get to the point. You know what you do? You do what's called, what 5.5 is all about is it's about this process called changing the variable. It's a change of variable gain. And we call that U substitution. And it's a technique, it's a process that you've got to get. U substitution. Substitution. Watch how it works on this. We said, oh, it's something cubed. We'll call that something U. So I go over here to my scrap paper and I say, okay, my U is going to be x plus 4. Now, I'm declaring that to be my substitution, okay? But that means I'm changing the variable from x's into u's. That means I got to change the dx into a du. The whole variable has to get changed over. So now watch this. Right here, what I do is a little baby derivative. If u equals x plus 4, I take the derivative of u and call it du. What's the derivative of a 1x? A 1. You guys are right.
1 du.
Dx.
Dx.
Is that bothering you? It's a dx.
Right.
What's the derivative of 4? Nothing,
0.
right?
Yeah.
Does this bother you? You don't like this? Take the derivative of u, call it du. Take the derivative of the x and call it dx. Can you handle that?
Right.
Yeah.
It's sort of the way we were talking at the very end of chapter 4 with our differentials. We were doing dy and dx kind of as separate things.
Right.
We kind of need that here. We call this du. Maybe you like, here, look, here, let me say it differently, although this is what, take the derivative of u with respect to x. Oh, okay, you want to call that du dx? What is the derivative of u with respect to x? What is the derivative? 1? But now I want to move the dx over here, actually. So du is dx, if you don't mind.
Yeah.
The truth is, I'm going to do that. I'm not going to do this. But maybe that helps you think about it. Maybe it's worse. Now what? I substitute this all back in. Look, erase the answer a second. I substitute all this back in. What does this become? Oh, this becomes a u cubed. Okay. What does the dx become?
Du.
The dx becomes a du. Okay, cool. Whew. Now it looks like a normal old power rule. And how do you do a power rule? 1/4 u to the 4th?
Mm-hmm.
Okay, 1/4 u to the 4th plus c. Problem over. Oh, wait a minute. Let's put our u back in terms of x like it should have been. The problem started in x's.
Right.
We temporarily use this new variable u to help me get the problem done. Now let's put the answer back in x's. So what's the answer? What was u?
X plus 4.
X plus 4.
4. Plus c.
Are you with me? You follow this? Now listen, and again, you're staring at this and you might think, like, we had that answer a second ago. Why are you going through all this trouble? I'm going through all this trouble because on this one, we got it wrong.
Right.
And so I didn't do a good job. When I did this one, I didn't do a good job of keeping track of du and dx relationship. I just sort of let you, here, let's do this one the correct way. You ready?
Mm-hmm.
Hang on, hang in there. What do you think you want to call u this time?
5x plus 8.
I think so. Let's call u 5x plus 8. Exactly. I mean, I want to call that u cubed. Okay, now, what's du this time? Du is the derivative.
5 years.
A 5 dx. Okay, all right, it spits out a 5, so to speak. I'm not doing a chain rule, I'm doing U substitution, but it spit out a 5. Now hang on, when I go to start to replace this, watch this, this is replacement, this isn't magic. Let's see what's going on. That's my U, so this is a U cubed. Now hang on, what's dx? I need to replace dx. What is dx? What is dx? What is dx? If I move the 5 over, 1/5 du, is that what dx is? You okay? You all right? That's algebra. So now I'm replacing dx with what it is. What is it? It's 1/5 du. The 1/5 is a multiplied constant. You can pull it out front if you want. And you're sitting here with a u cubed du. How do you finish? You add 1 to the power, u to the 4th, divide by 4. Don't forget there's a 1/5 out front, plus c. Are you guys okay? If you have questions, you can interrupt me. I'm not really that mean, just a little bit. The answer is 1/20 something to the 4th. What was that u? What was that u? What was that u? 5x plus 8. At the end, you plug it, you're done. From this step to this step, you integrate it. And we're done. But I should put my answer back in u's. So, I mean, back in x's. Hang on. I feel like I lost you. So when I lose you, you have to stay overtime. You ready for some overtime? It's not my fault. I lost you. I mean, you lost me. I mean, whatever. No, listen, I'm kidding. Hang on a second. Just bear with me here a second. What did I do the first time? I ignored this. And I just said, oh, well, that's a u, so it's a u cubed. And then so it's 1/4 u to the 4th. And so I just, I pretended it was something cubed, and I said the answer is something to the 4th. And what did I miss out when I did that the first time? Thank you. I missed the 1/5. Maybe you think it's trivial, but it's wrong without the 1/5. So it's not true trivial. And where the hell did the 1/5 come from? It came from the U substitution process. It came from the du dx relationship. That came from taking the derivative of this. Generated this 5, which ultimately came out as a 1/5. And so this U substitution process it's a process. And I want you to understand it. And this is just barely an introduction to it. There's a much more complicated one. Look at this. I mean, you could stare at this. I mean, anyway, right. Before U substitution, you could never do this problem. I mean, it's not an antiderivative. It's just a mess. But with U substitution, you can finagle this, play with this, and get it to where you can do it. What would you call U in this problem?
16 subtract x to the cube.
That's good. You're right. And then hang on. I'm not even going to finish this one, but if you're calling that U, which is good, what is du? Go ahead and tell me du, please. It's the derivative.
3x squared.
-3x to the 4th.
Negative,
Yeah.
the derivative. I'm doing it. See, here's the thing. I'm doing a derivative right in the middle of doing an integral. I'm doing a little derivative right here.
So negative 3x squared.
Negative 3x squared dx.
Okay.
Dude, now I got to start replacing this crap.
Okay.
I'm very happy, though, to see the x squared dx. Because I got this extra x squared dx
Oh, look at you.
in this problem.
Oh.
Here I go. I'm going to replace this. I hope I don't lose you. Watch this. What about this 5? What can you do with a multiplied 5?
Outside.
You could pull it out front. All right, hold on. What about this big square root thing? What is that? Isn't that just the square root of u? Okay, all right. I'm replacing this. All right, now watch this. What about this circle junk right here? This x squared dx. Can it get replaced? What is x squared dx? If I look down here, what is x squared dx?
3x squared.
It's du
Well,
over negative 1/3 du.
Negative 1/3 du is x squared dx. Is that okay with you?
Yeah.
So what am I doing?
So you're gonna replace.
I'm replacing this with
Negative 1/3
negative 1/3, which I pull out front, du.
du. Right.
That's cool, you guys.
That is.
That's good, advanced, medium U substitution problem. By the way, you're ready to integrate now. This is a u to the 1/2. How do you integrate a u to the 1/2? U to the 3/2 divided by 3/2. You're done with some stuff out front.
Okay, so.
All right, we'll get better at it. We'll stop. I'm stopping. We'll get better this Friday, I hope. But you got to catch up to me.